Hello everyone, welcome to this second lecture on electromagnetic induction. So in this lecture we'll be talking about the Lenz's law. Previously we have talked about Faraday's law, in which we have learned that whenever there is a change in magnetic flux linked with a loop or linked with a coil, in that case there is an EMF generated. Now today we will try to understand what Lenz's law says about it, or how Lenz's law associates that negative sign with the change in electromagnetic flux. So Lenz's law statement is, the law states that the induced current will appear in such a direction that it opposes the change in magnetic flux that has produced it. So what it means is that in Faraday's law, as already I have said in the previous video, that Faraday's law says us that the EMF induced E is directly proportional to the rate of change of the magnetic flux through the coil. But it cannot say about the direction. That means whether it will be equal to the negative of this or the positive of this. There is absolutely no idea about these things. But Lenz's law says that whenever you remove this proportionality sign, then you have to replace a negative sign here, and it should be like d phi upon dt. So what is the significance of this negative sign? Significance is that the induced current which will be produced in the loop, it will appear in such a direction that it opposes the change in magnetic flux. So for example, let's consider this diagram below. In this case, we have shown a magnet. This is a bar magnet and this is a loop. So whenever the bar magnet is brought nearer to this loop, in that case, what will happen? There will be a current induced in this loop, but in the very beginning, we do not know what should be the direction of the current. Now, the direction of the current according to Lenz's law should be such that it should oppose the change in magnetic flux linked with the coil. And how this will be done? Suppose the current is produced in the anti-clockwise direction. In that case, because of this current, the self-induced magnetic field, that means because of this current, the magnetic field which will be induced, those will be in this particular direction. So these are the magnetic lines of force that you can see here in black lines, black curves. These are the magnetic field lines due to this current I. All right. So these magnetic field come out of this surface and enter through this particular surface. So that means the top surface of this loop will act as a north pole and the bottom surface will act as a south pole. So see, this is exactly opposite to the previous bar magnet that we have chosen, because the bar magnet north side is facing the northern side of the loop. That means there are two northern sides now and they must be repelling each other. So the induced magnetic field or the induced current should appear in such a direction that the magnetic field which is once again induced because of the induced current should be opposing the original magnetic field. So that is why the current must be in anti-clockwise direction. Alright, this is what in brief the Lenz law says us. Now let's consider one more example, and by this example we shall try to understand how exactly Lenz law is associated with the conservation of energy, or whether Lenz's law has got any relation to conservation of energy. We will try to understand. So similarly, let us consider a coil and a bar magnet with north and south facing the coil as shown in this figure. So what we will see, whenever this bar magnet is brought close to this coil, gradually there will be an electric current induced into the coil and the coil will generate its own magnetic field. However, that generated magnetic field will be in such a direction that this end is north and this end will become south. Right? Now in doing so, the moment this end becomes north and this end becomes south, of course the magnetic field lines will come out like this. What will happen? You will face difficulty in bringing out this magnet towards the coil further. Why? Because this is the north side and this is also a northern side. So north they will repel each other, and ultimately we will face a difficulty in bringing this magnet further towards the coil. So there must be work done from our end in order to bring this magnet further closer to this coil. Alright, so this work done, or the mechanical work done basically, because not they are repelling each other, so if I have to bring it closer, in that case I must expend some energy. So that's a mechanical energy that I am expending from my source. So this mechanical work done in moving the magnet is changed into electrical energy, producing that electric current. All right. So whenever you bring the magnet slightly closer to this uh, coil, in that case, immediately a north-south pole is created. So if you have to further bring this magnet down to this coil, in that case, you have to spend some amount of energy from your own mechanical source, and that amount of energy is directly getting converted into electrical energy. Similarly, whenever you take this magnet away, what will happen? These polarities will change. Now this end will become south, this end will become north. So once again, south and north, they will attract each other. So since you are taking this magnet away now, so what will happen? This coil will try to attract the magnet down. So once you want to take it away, again you have to do some work against the attracting force. Previously you were doing work against the repelling force, now you are doing a work against the attracting force. So in any case you are spending some amount of mechanical energy, and that amount of mechanical energy is getting stored as electrical energy into the uh, system. So that is why it is quite true that energy can neither be created nor be destroyed, which is basically the principle of conservation of energy. So in this case also we have seen our mechanical energy is getting converted into the electrical energy in the coil. So therefore, we can say that Lenz's law is perfectly in accordance with the principle of conservation of energy. It doesn't violate the conservation of energy. Rather, we can say Lenz's law is a consequence of the conservation of energy. All right. So here there is a GIF image which has been taken from this source perfectly for educational purposes. So you can see this perfectly happening. So for example, this is a magnet. This could be say north. This could be south. Although it's not been demarcated, I mean in this particular video. So as you can see that it is bringing up, no, it's coming up out of this coil. What's happening? So when it is coming out, see immediately this current is shooting in the opposite direction, but since the magnet is at rest, the current is zero. So once again it starts going in, the current shoots up in the opposite direction, but again comes down to zero because the magnet is at rest. Alright, so this GIF video clearly explains the working of the Faraday's or the Lenz's law. Alright, I hope this part is clear. Now, there is one more important thing that is called Fleming's right hand rule. This is one very important thing. If we stretch the first finger, the central or the middle finger, and the thumb of our right hand in mutually perpendicular direction as shown in this figure, see. In that case, the first finger points along the direction of the field and the thumb is along the direction of the motion, if it is so. That first finger points in the direction of the field and the thumb points in the direction of the motion. Motion means motion of a conductor I am talking about. In that case, the central finger would give us the direction of the induced current. That means this will be the direction of the induced current. So in order to understand this, let's consider this diagram. Suppose this is the north pole, this is the south pole of a magnet, and this is a conductor where the conductor is being moved in the upward direction. However, the field is in absolute perpendicular to that. So these are like your thumb direction, and this is like your forefinger or the first finger. All right. So in that case, what will be the direction of the EMF or the induced current? This will be the direction of the induced current. So this is a very important thing. We call it Fleming's right hand rule. Similarly, there is an associated concept called Fleming's left hand rule. You can better see it for yourself. But at this point, I would like to stress, quite similar to Fleming's right hand rule, there is one more rule that is called right hand thumb rule. Many a time people confuses these two rules because both are right hand rules, and one is the thumb rule, another is known as the Fleming's right hand rule. So they are different actually. What the thumb rule says whenever you have got a steady current flowing through a wire, so this is a conductor through which a steady current I is being flown. In that case, there will be a magnetic field generated all around this coil, all around this conductor in a circular fashion. So if you point your thumb towards the direction of the current and curl your finger. In that case, the curling direction of the finger will give you the direction of the magnetic field surrounding this conductor. So this is known as the right hand thumb rule. So this is quite different from the Fleming's right hand rule and should not be confused. Alright, so whenever we have got current, we want to find a magnetic field, we will use right hand thumb rule. And whenever we have got a magnetic field and there is a conductor which is moving in that magnetic field, in order to find the direction of the induced current, we will use Fleming's right hand rule. Alright, so these are the two basic distinctions between these two things. Please do remember. Alright, so that's all I had for today. Next class we will come up with self-inductance and mutual inductance. So that will be discussed in the next class. Thank you so much.